Hi guys, in this video we will take a look at some chemistry of nitriles, and we'll pick up here in our handout with synthesizing a nitrile or a compound with a cyano group from a primary amide. This transformation involves dehydration of the amide. Removing H2O will give the nitrile. This can be accomplished using either thionyl or acetic anhydride or some other reagents, but these are the only two that we'll see here. Let's do this mechanism using thionyl. We'll also make sure we understand what the byproducts here are for this reaction. Okay, if you remember, the amides have high electron density on the oxygen. We talked about that because of the electron donation of the lone pair on the nitrogen. And the oxygen is actually going to be the nucleophile here. Okay? Now this is a case where the carbonyl group is acting as a nucleophile, where most of the time a carbonyl is an electrophile and nucleophiles attack it. But these electrons we can add to the sulfur. Okay, electrons up. That will give us going to be a positive oxygen now after one lone pair reacted. Electrons up onto this oxygen and two chlorines. There is a lone pair on that sulfur. We can realize that. We may not show it each time. By the way, this oxygen is going to leave this carbon. It's gone. How do you make oxygen a better leaving group? We can protonate it. We can also complex it with something, which is what we're doing here. At this point, why don't we reform pi bond and kick off a chlorine. We could do that. That would give this here. Now we could have also have done resonance at this point. I'll go to a black pen here. Because you might have said, well, which is a better leaving group, a Cl or a positive oxygen? Positive oxygen could be a better leaving group. Instead of doing that, we could have shown resonance here. These electrons move here, and these electrons move up. I'm going to draw out these NH bonds, okay? That's just resonance. Now at this point, we could have these electrons come down, and now we see that the chlorine is clearly a better leaving group than the neutral oxygen. Kick this off, and that would give That there plus Cl minus. Now this and this are the same thing. These are just resonance structures. Okay? Because I can go from here, take these electrons, move them in here, and move pi bond out. Well, that gives this. And of course, resonance structures are just two fake structures of the same molecule. So really, these steps are really no different. It's just which resonance structure do I choose to use whenever I reform the pi bond to sulfur and kick off the chlorine. You can do it either way you want. You can go this route or you can go this route. But this is a key resonance structure to get to. Okay? You can come this way and then do resonance, because this resonance structure shows a double bond between the carbon and nitrogen. Ultimately, we want a triple bond between the carbon and nitrogen, yeah? So we're halfway there. All right. Now at this point, I would use the chloride to deprotonate this. Let's come down here. And that would give that there. Okay. Plus HCl. And indeed, HCl is one of the byproducts that's formed in this reaction. We're actually going to get two HCl's, if you want to go ahead and show what's formed, plus SO2. Now that we have this lone pair, anytime we can use a lone pair to make a pi bond and kick off a leaving group, that's easy to do. This almost looks like a tosylate. It's only one oxygen on the sulfur, double bonded oxygen, and it's on a toluene group. But if we do that, what does this give? It's going to give the R. Okay, I'm going to start drawing in this carbon. And now we have a triple bond to nitrogen. Yay, that's what we want. There's an H there, and the nitrogen is now positive. And we kicked off the oxygen from that carbon. And that made, or generated, the leaving group, which was, or which is that there. Look how close we are to having the cyano group. We just need to deprotonate it. Well, we could use that, but this guy is going to, this molecule is going to, anytime we make a pi bond, kick off a leaving group, easy to do. That's going to give SO2, which has Lewis structure like that. We said we would form that, plus Cl minus right here. And the Cl minus will take this H, leave the lone pair on the nitrogen. Bonding pair moves to nitrogen as a lone pair. And there you go. We generate our product, a second HCl, and the SO2. Okay. Ultimately, we get something on the oxygen. Okay. Addition, elimination chemistry. Resonance at some point. Either before you eliminate or afterwards. It's really, strictly speaking, you'd probably want to do resonance as soon as possible, because at this point resonance is already there. But some books will show it this way. I would always show resonance as soon as possible, because as soon as you can show resonance in real life, it's already sort of there. It's already a delocalized system. Account for that. Then we can eliminate. The resonance gave us a double bond. All right, we take care of proton. Now anytime we can make a pi bond and kick off that activated oxygen, easy to do. That gets us the triple bond, and then we take care of proton again. So this is a way to make nitriles from primary amides. And we do lose water. Okay, it is a dehydration. We're losing 2 H's from nitrogen and the 1 oxygen, but we do not generate water. But it can still be considered a dehydration reaction. Okay, this reaction also can be done with acetic anhydride. It's very similar chemistry. You should practice that on your own. Okay. Now for chemistry of nitriles, for now, the only chemistry we're going to be looking at is hydrolysis of the cyano group, okay, back to the carboxylic acid. The nitrile sits in the box. Anything in the box can be hydrolyzed back to the carboxylic acid, either with aqueous acid or with aqueous base, okay. And in B here we see hydrolysis using, well, the first example is with aqueous acid, okay, and we're adding water to the nitrile. Now when you add water to the nitrile, you first get the primary amide back, okay, because in the previous reaction we removed water from a primary amide to give nitrile. If you add water back, you get the primary amide. And then the primary amide can be hydrolyzed to the carboxylic acid. We've already looked at that previous page. Amide being hydrolyzed to carboxylic acid. Mechanism here, we've not protonated a nitrile group. I'm going to redraw this with the Lewis structure. Okay, we've got H plus and water. First step here under acidic conditions is to protonate something. We're going to protonate the nitrile group, the only place we can here, and that is going to give the structure here, the protonated nitrile. That makes the nitrile carbon. All right. Again, nitrile or cyano, either term can be used. when we're talking about this group here. It makes the nitrile carbon more electrophilic because this nitrogen is now pulling even more. Nitrogen wants these electrons even more since we made it positive, and it really makes a good amount of partial positive on the carbon. We talked about this for carbonyls, but it also applies for the cyano group. And at this point, water, which is a fairly weak nucleophile, will react at that carbon, and we can move those electrons over to the nitrogen to give the nitrogen what it wants, and that will give this bond here being made. We now have double bond to nitrogen, lone pair, and H. Nitrogen now becomes neutral. We get to this. We get our oxygen on the carbon. We eventually want to have a carbon double bond to oxygen. We also want two H's on the nitrogen. At this point, we can do a proton transfer. Why should the proton sit on the oxygen lone pair? Why can't it sit on the nitrogen lone pair? Indeed it can. That's going to give this. Okay. And yes, you saw that. We're missing a positive charge on nitrogen. Nitrogen is now protonated instead of the oxygen. At this point, we can consider resonance. These electrons move in here. These move out. And that will give a resonance structure Now we look a lot like our amide. We just need to remove the H. Okay? And whatever acted as the acid, there's got to be a negative here that could take the H and reform the acid. Okay? So the acid is our catalyst. Now, if you're going to keep going, I would not remove the H and go neutral, because you're just going to turn around, and if you're going to hydrolyze the amide, the first step is to protonate the carbonyl. All right? It's already protonated. So at this point, if we want to hydrolyze again and have another water come in, we would just do that from here. Protonated carbonyl, electrons add. Okay. I'll keep going a little bit. That will give that there. What are we trying to do? We're trying to eventually eliminate off that nitrogen. Well, let's do a proton transfer. Why does this oxygen lone pair have to be protonated? Why not protonate the nitrogen lone pair? It's actually more basic. Get to this point. We see that these OHs are equivalent. We can use either one of them, and anytime we can make a pi bond and kick off a leaving group, easy to do. And that will give, I'm going to not draw that carbon in. Well, I can, it doesn't matter. We now have double bond here and an OH plus NH3 leaving group. Now at this point there's a minus that could take this H to go neutral, but ammonia is actually a stronger base. Let's use ammonia to take the H, leave this behind. Okay. And we will get our products as shown above. The carboxylic acid and the ammonia has taken an H. Because we're under acidic conditions, we expect the ammonia, which is a base, to exist in the protonated form. Alright. And the minus here would just be whatever minus was with your acid. Alright. This could have been aqueous hydrochloric acid, so there's a Cl minus, and so you would have made ammonium chloride. You're not going to reform HCl with ammonia around because ammonia would just react with the HCl to make ammonium chloride. So you might as well just go ahead and make ammonium chloride directly. And that's what we did. Okay, so we just keep working to get to where we need to go. Classical carbonyl chemistry. All right. So again, the primary amide is sort of the possibly isolated intermediate. All right. But it can be further hydrolyzed to the carboxylic acid. In the end, we converted the nitrile, or we hydrolyzed the cyano group to the carboxylic acid. This was, of course, if you remember, also shown originally when we used the cyanide as the synthon, carboxyl synthon, do an SN2, and then we can hydrolyze the cyano group to the carboxylic acid. But there are other ways to get to synthesize nitriles. Okay, you can also hydrolyze the nitrile group using aqueous base. All right. Again, the first hydrolysis gives the amide, primary amide, and then you can further hydrolyze that to the carboxylic acid. If you're under basic conditions, that'll exist in the basic form. You should give that a try on your own. Keeping in mind there's no proton here to protonate the cyano group. Okay? Alright, we only protonate things with strong acids. But here you have a stronger nucleophile. Instead of water, okay, here you have hydroxide as the nucleophile, and it is strong enough to react with the cyano group. Pure water is not. Water will only react if you first protonate the cyano group. Okay. Now down the road we'll do a little bit more chemistry with nitriles, but for now that's kind of it. All right. This sheet is a miscellaneous topic which talks about carbonic acid. just a little bit of kind of miscellaneous information, but important. This molecule here is sort of like a double carboxylic acid. It's called carbonic acid. It is not stable. Okay? It will break down to form water and CO2. All right? It's not a stable acid. Now, this is CO2 is a gas. If this is open and the gas escapes, this is going to be pulled to the right completely as the CO2 escapes. All right? But if this is in a closed container, these two will actually react and form an equilibrium, and carbonic acid will exist in the closed container. You open up the container like when you open up your can of Coke and it goes psh, CO2 is released, the equilibrium adjusts, and the carbonic acid will all go to the right as the CO2 escapes. So it really only exists in a closed environment. All right. Now, monoacid derivatives are also not stable. This sort of acid-amide mixture, not stable. All right. It will break down into ammonia and CO2. Ultimately, because anytime you can make a pi bond and kick off a leaving group, that's easy to do. We can do this mechanism like this. That will give although there's a lot of hydrogen bonding going on here, and maybe a proton transfer takes place first, I'm going to just do it like this. Okay. And then this takes an H, and there you go. You get, so you're kicking off these leaving groups here. All right. Again, I don't know that this is actually going to be formed, but I'm just kind of giving you a general idea. All right, so neither of those are stable. Now, there are some derivatives of carbonic acid that are stable. The diesters are stable. All right, this is called diethyl carbonate. That name comes from because if you just look at this, that is carbonate. That is CO3 2 minus. All right, polyatomic ion. You learned in Gen Chem. You can have like sodium carbonate. All right, like Na2CO3. That's just where two sodiums sit here. If you put ethyl groups on each of these, it's called diethyl carbonate. Of course, the ethyl would be covalent, and so that's a fully covalent molecule, where sodium carbonate is ionic. All right. Now the dichloride is stable. That's actually it has a common name of phosgene. It's actually a very reactive molecule. It's a gas. All right. Now, acid chlorides are very reactive. Imagine the reactivity of sort of a double acid chloride. That carbonyl carbon is very electrophilic. All right. And proteins in your body will start reacting at this carbonyl. Because it's so reactive, phosgene has been used as a chemical weapon. All right. It actually also was mentioned in one of the James Bond movies, where they're in a cave and they start smelling this gas, and somebody says, or maybe even James Bond says, "It's phosgene gas." and they try to escape the cave. Okay, the diamide is stable, all right, and you have heard of it before because the name of this diamide is, anybody know it? Is urea. All right, and some mixed derivatives are stable. This is sort of like an amide ester. All right, it's called ethyl carbamate, much less common than maybe phosgene or urea or these above. All right. Now here again I'm showing the sodium carbonate. I showed that above. You can also have sodium bicarbonate, just one sodium. That's where the other oxygen is protonated. Okay. And you know from 3rd grade where you can make a volcano with sodium bicarbonate, baking soda, you react this with H+. All right, this is plus and this is minus. What happens? The anion here gets protonated, and that leads to carbonic acid. It's not stable, right? It breaks down to water plus CO2, and the CO2 will start bubbling as it is evolved from the solution or mixture. Okay, and that's how you can create a volcano in which you may have saw in elementary school. You can do it in your kitchen. Take baking soda and add it to some vinegar, which is going to be a proton source. Yeah? Okay, so that's just a little overview of carbonic acid derivatives. Carbonic acid itself is not stable. Really, nothing with the OH is going to be stable. But some other type derivatives, like with the double ester, double acid chloride, double urea, these are stable. And note that these are all at the same oxidation state. In each case, the carbon here is bonded to 4, or has 4 bonds to a more electronegative atom. All right, 4 bonds to a more electronegative atom in each case. So it's not a carboxylic acid derivative, because a carboxylic acid derivative, the carbon only has 3 bonds to a more electronegative atom. Okay. The next miscellaneous topic in this handout, and to finish this up, is a look at some condensation polymers. All right. Take a look at this, how we can get chemistry and polymers, in this case nylon. Okay. We'll talk about this in class a little bit. Take a look at this yourself. Kevlar is a condensation polymer. Condensation because when this polymerizes, you're going to lose water, and the water can be condensed out. That's where that term comes from. These can also be called polyamides. Okay, nylon 6 is a polyamide, amide. Kevlar, only one amide group is shown, but if you show the repeating unit, it's going to be amide, because this is bonded to the carbonyl. All right. In addition to polyamides, you can also have polyesters. Okay. You've heard that in terms of clothing, polyester shirt or polyester pants from the 1970s. All right. dacron. Okay, it's a single monomer. Something like this one here, Codel, is 2 different monomers. All right. We can look at these in class a little bit, but please take a look first. And then another polymer that we can look at is peptides in biochemistry. It's actually a polymer where the monomers are amino acids. And it can be a variety of amino acids. And when you make your polymer chain, it's called a peptide. And each monomer, the R group can vary depending on which amino acid was incorporated into the peptide. But it's also a condensation polymer because you will lose water. Okay, see what type of questions come up with polymers, but it's a good application to think about with carboxylic acid derivatives. These types of polymers. These are polymers that come from carboxylic acid derivatives. You can also have polymers from alkenes or maybe epoxides, etc. Okay guys, we'll end this video here. That pretty much finishes up this handout. Next video we'll be moving on to the simple addition handout.